Hi, I'm Marty Kelsey, one of the hosts of STEM in 30, an Emmy-nominated TV show for middle school students produced by the National Air and Space Museum. This program is called What's New in Aerospace, and boy, do we have a brand new topic to talk about today. I am so excited. On Monday, an international team of scientists announced that they had found the presence of phosphine in Venus's atmosphere. Now, this is a big deal because phosphine is associated with life. But as with all good science, this has to be independently verified or refuted. But how exciting is this? So today, to help us learn a little bit more about this, we have one of the authors of the paper that was released in Nature Astronomy, Dr. Sukrit Ranjan, a postdoctoral fellow at Northwestern. Thank you for joining us today.
Thank you very much, Marty. It's a real pleasure to be here today.
All right, now I want to remind everybody watching online, let us know where you're watching from. We would love to give you a shout out during the program today. And let us know what questions you have. There have been all kinds of articles that have come out about this, and I'm sure you've got questions. And so I'm going to start today with Sukrit. I got to know, did we find aliens on Venus?
Unfortunately, Marty, we did not find aliens on Venus. What we think we found on Venus is a particular kind of molecule, a particular kind of gas called phosphine, which consists of a phosphorus atom bonded to 3 hydrogen atoms. This is a gas we didn't expect to find there. No one predicted it previously, and if you do kind of first order calculations, you don't expect it to be there either. We tried to do a bunch of calculations to explain why that gas was there, thinking about different mechanisms like lightning, impacts by meteorites, volcanism, atmospheric chemistry, processes like those. And our efforts to explain it so far have come up 0. So what we're left with right now are either we've made a mistake somewhere, which is possible. We've made our data available to the public, and we've also published all the details of our calculations online. Or there's some kind of physics and chemistry which we don't know about, which is very possible. There's a lot we don't know about Venus, and even more we don't know about the photochemistry of about the chemistry of molecules in the absence of oxygen, and in particular molecules like phosphorus-bearing reduced species like phosphine. Or one of the other kind of backup ideas we have is that we do know one case in which it's synthesized on a terrestrial planet, our own, and there it's synthesized by life, which is the basis of the suggestion that perhaps one of the backup options might be life.
Awesome. So let's back up a little bit. Tell us, what is phosphine and how does that connect to life?
Certainly. Phosphine is, again, a gas, a molecule that consists of a single phosphorus atom bonded to 3 hydrogen atoms. That's not the state in which you expect to find phosphorus on the surface of Venus. Venus has a lot of, it doesn't have a lot of free oxygen, but it has a lot of oxygen atoms in its atmosphere in the form of molecules like CO2 and SO2. And you similarly expect to find P there bonded to other O's, not to H's. So that's what's weird about it. Here on Earth, PH3 is produced in a few different ways. It's an industrial byproduct in a number of applications, so it's produced by us. And in the absence of humans, it's also produced by what we call anoxic biosystems. That is to say, living systems in the absence of oxygen. These include intestinal tracts, species of various kinds of animals. It also includes things like wetlands, the interiors of wetlands, which are relatively low oxygen environments. Those are the places from which we've seen phosphine production before. And so it's just by now, we also see it elsewhere in the universe in the gas giant planets like Jupiter and Saturn. And we think we understand the reason for their formation there. It's because those planets have a lot of hydrogen, and they have very hot and very high pressure conditions in combination with that hydrogen, which are not available on Venus.
Awesome. All right, well, we've got folks watching from all across the country: Columbia, South Carolina, Kenosha, Milwaukee, Elkhorn, Wisconsin, San Francisco, and San Jose, California, Oregon, Dallas, Kilgore, Texas, a bunch of homeschoolers. Thanks for tuning in. Tucson, Arizona, Akron, Ohio, and a bunch more. Keep those coming in, but also let us know what questions you want to have answered. We've got an expert with us, and so let's try to stump him today. I think that would be kind of awesome. All right, now we've got a question here, and it's a little bit of a deep dive, so bear with us. If we were able to send a probe to Venus and verify these spectral measurements with direct samples of the atmosphere, how will that impact our interpretation of spectral measurements from faraway exoplanets that we can't visit?
That's a great question, and I'll answer it in 2 regards, 2 ways. First, we do need more confirmation that there is in fact phosphine present on Venus. We've identified one spectral feature, one kind of fingerprint of light of phosphine, but really we would like many more to make sure that it's really phosphine there and not some other molecule or some other fingerprint that we don't know about masquerading as that. So a probe would be really great to make sure that probe is kind of the gold standard in making sure that phosphine is really, really, really there. Although there's other stuff we can do before that with with telescopes and things like that. If we know that phosphine is present on Venus, then that tells us that phosphorus-bearing gases like pH3 are present on terrestrial planets, and we can add those to the inventory of gases we can look for on planets orbiting, rocky planets orbiting other stars, like great missions like TESS and Kepler have discovered so many of. One significant caveat I'll point out is we looked into the problem of detecting phosphine on planets, on rocky planets or on other stars, and we concluded that it's actually going to be very hard. The big problem with phosphine is that it's very reactive. It's very easy to destroy. It's destroyed easily by UV-driven processes. And that means it's hard for it to build up to the really big concentrations you need in order for it to be detectable all those billions upon billions of miles away on planets orbiting other stars. So it's at the realm of doability, but it would be really tough, and your biosphere would really need to choose to make phosphine at gigantic fluxes in gigantic quantities. So it's a tough observation. Wouldn't bet the house on it right now.
These observations were made from observatories here on Earth, right? In Chile and in Hawaii. Why use those observatories rather than like the Hubble Space Telescope or something that's outside the atmosphere?
Those are really great questions. The key thing about the observatories that we use is that they worked at radio wavelengths. Hubble works at optical wavelengths. It works in the near infrared. It works in the UV. It works at much shorter wavelengths. The strongest feature, the most favorable feature of phosphine to detect in the atmosphere of Venus is present in the radio. And the best radio telescopes are all present here on Earth because you can build them a lot bigger. And size really matters for radio telescopes.
Awesome. All right. Does this, you kind of mentioned this earlier, does this have implications for other planets in our solar system, Jupiter, Saturn, that are those gas giants? Does it have any implications there?
Not as much, because we all already detected phosphine on those objects. On those objects, phosphine is present due to so-called thermal equilibrium chemistry deeper in the core of these objects. So in the further down in their atmospheres, it's really hot, it's really heavy, there's a very high pressure, and there's a lot of hydrogen. And these factors combined mean that you can make phosphine down there completely in the absence of biology, purely what we call abiotically. And then vertical mixing, atmospheric turbulence, can transport that up to the upper atmosphere where it can then be detected. In fact, that's what phosphine is used for in those atmospheres. It's used to measure the vertical transport.
Okay, so that's how phosphine goes from more the surface area up through the atmosphere?
Deeper in the atmosphere. They don't really have surfaces as much, but like from the deep atmosphere to the upper atmosphere, we can look at how fast phosphine is being transported, and we can use that to kind of see, measure the speed. It's like, I don't know, it's like a chemical speedometer kind of deal.
Awesome. Was there any aha moments as you were working on this paper where it was like, wait a minute, this is a thing? Or was it more a slow, tedious process pulling that data out and coming to that conclusion?
There's two sides to the work. The first is the observational side, actually trying to detect the molecule, and the second is the interpretation, trying to figure out what could be creating this putative signal. There were, I feel, I can't really speak to the observational side as much because I wasn't involved with that, but from what I understand from my colleagues, kind of the moments where they first kind of realized that they had a signal and it looked like a real detection. And when they got the ALMA follow-up confirmation at much higher quality, I think those were very exciting moments for them. On our side, it was more a giant slog as we just kind of tried to get together and brainstorm, can this make a lot of phosphine? This isn't working so good. What about this? What about that? Oh, I don't know how to do that. I guess we got to do some reading, all that kind of stuff. Long slog for us.
That's awesome. All right, we've got folks from Herndon, Reston, and Richmond, Virginia, Maryland, Kenton, Delaware, Westfield, Massachusetts, Seattle, Washington, Nebraska, Garden City, Kansas, Long Island, New York, St. Louis, Missouri, Chicago, and Honolulu, Hawaii checking in. Thank you all for tuning in. Also, we've got from around the world, Belgium, Italy, India, and Cape Town, South Africa. Thank you guys so much for tuning in, and let us know what questions you have down in the comments section. We've got another question that came in. Someone wants to know what new questions need to be investigated in light of these new findings.
Oh boy, this is a dangerous question to ask me because what I tell folks is that more than anything else, this finding we have is a call to future work. I would kind of group it into two or three main questions. One, on the observational astronomy side, we really want to make sure that phosphine is there. So we want to detect other spectral fingerprints of the molecule, either remotely or from a mission that goes closer to the planet. The second is we want to understand its chemistry a lot better. We don't actually know very much about the chemical processes involving the family of molecules to which phosphine belongs. We know the thermodynamics, but not the kinetic processes, not how fast it goes. And so we'd like to measure those processes a lot more so we can improve our computer models and really reduce our uncertainties and really increase our confidence, really understand better or not whether the abiotic mechanisms we're aware of can explain these phenomena. Additionally, we'd like to improve our understanding of the biochemistry of phosphine here on Earth. We've seen that it's associated with biology, but we haven't elucidated the precise enzymatic pathways by which it's produced, which would be useful to understand a little bit better. So those are, even before we think about sending missions there, those are investigations, further observations, laboratory chemical studies, and laboratory biological studies, I think are all worth doing.
So like all good science, this doesn't answer the question, it leads to many, many more questions.
Yes, I would very much treat this as a trigger more than any kind of final seal.
Awesome. So if there are kids out there watching, this is an area you can go into because there are all kinds of new questions that need to be answered here.
A lot of them.
We got a question. Someone wants you to explain, how did we get this signal? We've got a graph that kind of shows the phosphine in the atmosphere. How did we find that? Like, what's the basic that we got there?
That's a really great question. So you have the planet Venus. The planet Venus is always radiating out starting from its surface, going upwards a certain amount of radio waves. Suppose you have a molecule that's present there, like phosphine, at a very particular wavelength, with a very particular size of light. That molecule phosphine will absorb that light, so that you kind of see that as a little bit of a dip in that spectrum. So what you're seeing there is that at a very specific wavelength, at a very specific size of light, there's less radio radiation from the planet. The location of that dip is very sensitive to which molecule you have. So they're often treated as kind of spectral fingerprints, a way you can, where that dip is, you can use to identify what that molecule is. And so that's the process of, that's kind of the method by which phosphine was detected. The lead observational team, led by Dr. Jane Greaves, knew roughly where they expected to see it absorb if it was there. They looked, they saw absorption when it was there, and then they spent a whole lot of time trying to convince themselves that it wasn't made up. And also that there wasn't other stuff that we're aware of that could be masquerading there, kind of spoofing that fingerprint.
I think one of the interesting things for me talking to you is hearing you talk about, you tried to come up with all of these ways that you were wrong and figure out what could this be other than, potentially life. And I think going through that process is really interesting. Were there sessions where you all were just spitballing ideas about how you could be wrong on this?
Oh yeah, of course. That's the most important thing to do. Like, this is something I learned very early in graduate school. My first graduate school project, we had our core results within like a few months. And then the project dragged on for another 3 years, all of which was basically us trying to figure out different ways we could be wrong and trying to test that. So I think that's a very important part of science, is healthy self-skepticism and trying very hard. Basically, the more exciting the result is, the more hard you need to assume that you're wrong and try to prove that. And only when you don't do that can you kind of advance to the next step and maybe contemplate the idea that maybe you should think a little bit about more exotic things.
All right, now you were talking about the spectrum earlier, and I want to see if I've got this right. So I'm wearing a black shirt, and that means that light that's hitting this shirt is being absorbed and not really reflecting the colors, where the white is actually reflecting all of the colors back. And if I see green, that's, reflecting the green back. Is that kind of the same thing that's going on here with the phosphine, only at different wavelengths?
Exactly correct. Yeah, it's a very similar process that's going on, just at different wavelengths. And in this particular case, your shirt is opaque. Light reflects off it, it doesn't pass through it. But atmospheres are often largely transparent. A lot of the light will pass through them. So here it's kind of more like a filter. Like you might have stained glass, which only allows certain filtered wavelengths of light through.
Awesome. That's a great analogy. Somebody asked, are there other gases from the oxygen deficient life forms that we could also detect on Venus?
This is a great question, and it's a really funny question because that's one of the questions that our team is very interested in. One of the questions that our team is interested in is evaluating the various different gases that life makes, particularly non-oxygen using life, more similar to what early Earth had, and evaluating them as potential biosignatures. We don't have any good reason to suspect that they're there on Venus, and in fact, many of them I think have been looked for already, and they're not. But then a priori, had you asked us, is it a good idea to look for, had you asked our theoretical team, is it a good idea to look for phosphine on Venus? We would have been like, that seems a bit remote. I probably wouldn't bother with that if I were you. So I think this is a case where nature could surprise us. So as always, science is data driven. It's always better to think, what if, and go look, as opposed to be overly wedded to theoretical ideas.
Awesome. All right, we've got a question that came in. Is the creation of this phosphine solely a result of biological origin, or is there something else that's potentially going on there? And you kind of mentioned maybe something that you don't understand yet.
Absolutely, yeah. We're definitely not saying it's a biological origin. We're just saying that of the mechanisms that we have evaluated to explain it so far, we don't know what they are. So the other mechanisms that we haven't yet completely ruled out are something unknown, or some form of biology. But when I think sometimes when scientists say that, oh, there's something unknown we don't know about, sometimes people think that's a little bit of a fig leaf. You're just doing that to like cover all the bases. That's not the case here. What we really want to emphasize is that chemistry in the absence of oxygen is very understudied. And that's because it's not really relative to your life and my life here on Earth, where there's lots of oxygen. It's only folks who are interested in other planets and things like that spend a lot of time, or exotic industrial processes that work a lot on that. And so there's a whole bunch of question marks about the chemistry of phosphine and about related compounds and mechanisms that we just don't know. And in our paper, we actually kind of published lists of, here's a bunch of the laboratory studies and the kind of computer modeling studies and stuff we'd like to see to be done to improve the state of our ignorance. So what we really want to emphasize is that in contrast to gases like O2, where we really understand the behavior really well, there's a lot of things about pH3 phosphine that we don't understand. And so we really want to emphasize that the idea that there's something that we don't understand is really a big one. It's not a fig leaf, it's a mainstream. It's what we'd focus on first.
And if you want to check out this paper, we're going to post the link down in the comments section, and you guys have awesomely made it available for everybody to go through and read. And I will say, I read a bit of it, and it's a tough read, but it's pretty interesting to get in and really see the work that went into with coming up with these findings. And that leads to the next question. Somebody wants to know, how long have you all been working on this project?
Different folks have been working for different amounts of times. For example, the study in Scepter, Dr. Jane Greaves in the United Kingdom, I think, I don't know exactly how long she's been working on this, but I think 2015, 2016, something like that. Some of our other colleagues have been working on it going back 2012, 2013, that kind of stuff. This particular project, analyzing phosphine specifically on Venus, I think started about maybe 3 years ago, 2 or 3 years ago.
Okay, somebody wants to know about using missions that went to Venus. The USSR sent missions to Venus previously. Was any of that data used as a springboard for this research, or was this all new?
Oh gosh, yes. Yeah, we very much, as with all science, standing on the shoulders of giants, that's what we do all the time. Yeah, the various missions by various nations, especially the USSR, were absolutely critical. One of the most interesting results came from their landers, which the naive result from if you just take their kind of measurement device and you look at the raw measurements from it, it suggests that there's a whole lot of phosphorus in the lower atmosphere of Venus. And I think maybe that was actually kind of ignored for a little bit. I certainly don't remember seeing models of the photochemistry of the Venus atmosphere that included phosphorus-bearing species. I think people were all a little skeptical. They're like, well, phosphorus is in paint as well. Maybe some paint got stuck in the sensor or something like that. So, but when we went back and tried to analyze it, when we tried to see, could this molecule realistically be there? Measurements like that were really key to say, there is some phosphorus there. It's possible that it could be converted into this weird form. And of course, measurements of the temperature, the pressure, all the different molecular features, those were really critical.
Awesome. All right, well, we've got more questions coming in. We've got a little bit of time left, so be sure to put those questions down in the comments section. We've got the United Kingdom, Gibraltar checking in, Santa Fe, New Mexico, Corpus Christi, Texas, Jupiter, Florida. I'm glad that they put that on there, Jupiter, Florida. Chambersburg, Pennsylvania, Chapel Hill, North Carolina, Sacramento, California, Arkansas, and Oklahoma. Thank you all so much for tuning in. Hope you're enjoying the show today. The next question we've got is, somebody says, I know some of the space missions currently competing for funding through the decadal study would go to Venus. Would any of those missions help out confirming your all's findings?
That's a really great question, and I know some very smart people are looking at that question right now. I don't know the answer to that question. Those things are kind of it's hard to turn them on a dime because they have very elaborate, very intense planning procedures going on, but I think they're certainly looking into it. For me, what I would tend to focus on is, before we even think about missions, which won't launch for like 5 years or 10 years or something like that, there's a whole bunch of work that we can do right here on Earth in our laboratories and with our, in silicon with our computers, to kind of measure the fundamentals of these chemical uncertainties that we highlight in our paper. So people jump to missions. There's a whole bunch of stuff we can do with the great universities and research facilities we have in this country and across the world right here, right now.
Awesome. And that leads us perfectly into this next question from a loving science person from Michigan. So thank you for tuning in. They want to know, what are you most curious about right now with the current information, and what are you looking forward to learning?
What I would like to know the most about is, I would like to have a better understanding of the photochemistry, of kind of the composition of the Venus's atmosphere. Right now, the kind of computer models we have do a decent job, but not a great job. They can't explain all the features we see there. For example, they have a lot of trouble reproducing the high atmosphere water vapor content in that atmosphere. And there's a whole bunch of other uncertainties that are buried into those models. So what I would really like to do is get much better laboratory measurements of rate constants and how fast these reactions go, so we can build better computer models and get a much better picture and a much better understanding of the chemistry of this planet and how it works.
Now, you mentioned earlier that you all tried to come up with all of the different ways that you could be wrong on this, but can you talk a little bit about why you used the 2 different observatories and 2 different times during the year to do the observations?
Sure. Part of that is practical. ALMA is a really competitive instrument. If you tell them that you want to look for a gas on Venus under with the scientific case that it's a biosignature, you better have some kind of other detection first before they'll give you the time on it. And the folks at the James Clerk Maxwell Telescope were really kind of visionary and kind of accepting the science case and saying, yeah, no, it's a high risk, but let's give it a shot. So that's part of it. But then there's also immense value to using different facilities in different locations and at different epochs. Because one of the things you always worry is, did we screw it up in some way? And if you just have it from one facility, well, the question is, well, was there something particularly weird happening at either Earth or Venus or somewhere in between that day? Was it some kind of like weird thing in that telescope that particular day? Maybe someone bumped it wrong and it did something weird. Is it something particular to how we cleaned up the data from that instrument? Are we introducing an artifact, a fake signal somehow? So if you have different facilities in different locations at different times, whose data you analyze in different methods, that increases the probability that what you're seeing is a signal legitimately from Venus, as opposed to some kind of mistake that you've introduced.
Awesome. Sounds like you all have done some really great science to get to these findings, which is always fun to hear about. Somebody wants to know, does this mean that phosphine may be on more planets or more common than originally thought?
It certainly does, in the sense that I don't think it was always kind of the idea that you had kind of on rocky planets, not gas giants. Gas giants we know have had phosphine for a long time, because it's produced, we know how it's produced there. But on rocky planets, the idea that there should be a ton of kind of atmospheric phosphorus, I think that was certainly in advance of this project, and I would have thought that was a very radical idea. So if this gas continues to be confirmed to be there, I think it's going to really change the way we think about the atmospheres of rocky planets.
Awesome. So somebody else wants to know, how do the clouds mess with the spectral measurements on Venus, and does that same thing happen on exoplanets?
That's a really great question. I think someone's been doing a lot of really intense reading out there, whoever that is. The short answer is that I don't have a clear sense of how the clouds interfere with the measurements for this observation, because I don't know much. I'm not a specialist at the radio wavelengths. Those are my colleagues. For exoplanets, it's a little bit different. It's much harder to get radio measurements from exoplanets, and so that's not really a target. Where it's going to have to be at shorter wavelengths, like in the visible and the IR. And their clouds are really quite quite unfortunate. They're not very transparent there. They are very opaque. They block a lot of light, and they're going to really cut down our signal quite a bit.
All right, now we've got a question that I think might stump you. We've got Zia, who is 7 years old, and she wants to know if astronauts are sent to Venus, do they need special suits, and how are they going to protect themselves from the sulfuric acid?
I think if astronauts are sent to Venus, OSHA is going to have a field day. OSHA is kind of the government agency responsible for health and safety of workers. Venus is not a good place for life as we know it. Venus is a very, very, very harsh environment. The surface has been described as analogous to, forgive the language, hell, in the sense that it has 90 bars of pressure, so 90 times as much pressure as we have here, sitting here on Earth. And it's at 700 Kelvin, so that's like 400 Celsius. It's boiling, boiling hot. It's enough to melt lead. It slags anything that lands on it. The clouds are a little bit better in the sense that you have liquid water there, and it's temperate. It's only 60 Celsius, as opposed to 400 or so. But they're still not great. In particular, the water droplets there are the droplets there are 90% sulfuric acid, and so it's very, very acidic, and there's very little water available. So it's a very harsh environment. So I think we talk a little bit about Venus's clouds having all the ingredients. Sometimes you hear people say Venus's clouds have all the ingredients for habitability, in the sense that they have liquid water and they have some of the basic elements and maybe some energy. But life as we know it, like anything we don't have anything on Earth that can survive that. So life is not a natural explanation. If there is life there, it is totally different from anything we know about. And it's going to be very exotic and very different. If it's there, which is a big if, no means certain, not the natural hypothesis, we could learn a lot from it.
Awesome. Well, Zia, good luck on your quest to become an astronaut. Maybe Venus is not the first place that you want to go visit, but good luck on there. I hear the moon and Mars are both nice, and you're at the right age to potentially be that first person to step foot on Mars, which would be awesome. And remember what's new in aerospace and the National Air and Space Museum when that happens. I want to talk a little bit about the idea that there is life floating in the atmosphere there. Is that something that we see here on Earth, or is that something completely new?
That's a relatively recent thing here on Earth, and it's a topic of investigation that has been underway for some time, but hasn't gotten quite as much attention as I think it deserves, and I think hopefully it'll get a little bit more now. The short answer is that there's definitely life in the clouds on Earth. The question is, can it fulfill its full life cycle in the clouds? In other words, can it always stay up there without ever having come down to Earth, be fully aerial? And my understanding is that the current thinking is that for the life on Earth, the answer to that question is no. I don't believe life in the clouds has ever been observed to reproduce, although maybe I'm a little out of date on that. So the full life cycle, and I don't know if we've done all the work required to investigate that in full depth. There's a lot of great folks, for example, at NASA Ames, who are investigating those very questions. So the answer to your question is that I don't think it's been fully demonstrated, but take that with a grain of salt. It's not my area of expertise.
Awesome. Well, we've got a few more minutes. Be sure to put those questions down in the comments section. We'll try to get to as many of them as we can. Somebody wants to know, how long does phosphine last? And are the molecules you discovered really old, or have they been produced recently?
That's a really great question. And let me tell you our thinking about it a little bit. We are very confident that in the high part of Venus's atmosphere, where there's a lot of UV radiation loves to go in and blow up molecules, basically. And when those fragments of those molecules are energetic and they go on to blow up more molecules. So we're very sure that in the upper atmosphere of Venus, the lifetime of phosphine is very, very short. It can be less than 1,000 seconds, less than 1 second. It can be very, very short indeed. In the bottom of the atmosphere of Venus, or in the middle bottom of the atmosphere of Venus, it's protected from light. And it's also not really that hot. So it's possible that the lifetime of phosphine molecules could be quite long there, on the order of centuries or perhaps even longer. The big issue is that those two areas are connected. In other words, if you stick a molecule in the middle of the atmosphere, it can't just stay there. It circulates, it moves around, and we know that to some degree. We've observed traces of that motion. So our belief is that the ultimate lifetime of those molecules on Venus is limited by transport to the upper parts of the atmosphere. That provides an upper limit, a maximum lifetime.
Awesome. All right, somebody wants to know, would extremophiles be able to exist anywhere on or above the surface of Venus?
Oh gosh, no, nothing we know about it can at all exist there. I think, even the most extremophiles we've measured so far here on Earth don't have conditions that are quite as hostile as are present on Venus. I'm not even sure if conditions that's hostile on Venus exist even in the most extreme niches on Earth, although I'm willing to be enlightened there. So yeah, nothing we know on Earth can exist there. Life is not a slam dunk explanation for the signal we see.
Can you tell us a little bit about the team that you worked on and who all's on that team and kind of how you all came together?
Certainly. The team that we worked on is a really great team. I'm very proud and privileged to be a part of it. And one of the special things about it is that it's extremely interdisciplinary, because to answer these questions about biosignatures and rocky planets, you really need input from all the disciplines: physics, chemistry, biology, geology, all that stuff. And so we have a couple of folks who come from a more chemistry or biochemistry background. We have a few folks who come from an astronomy background, planetary science background, strict spectroscopy background. On the other side of the pond, our UK team has a lot of really expert observational astronomers, plus some earth scientists and photochemists and things like that. So it's a very broad range of expertise. And one of the things we have to learn about is learn to speak each other's languages and learn to respect each other and learn how to ask each other intelligent questions and figure out where are some of the gaps that we have and what are some of the questions we need to address.
Awesome. I love that you said that, because I feel like a lot of people are doing a lot of virtual work right now, and both students and adults, and I think asking those good questions is incredibly important. We've got one more question here that I want to kind of wrap up on, and I think this is a great one to end on. Somebody asked about advice that you would send to students about persevering while researching. So, did you guys hit any bumps along the road, and how did you keep going on that? And what advice would you have for those students?
Oh gosh, yes. I think this is a universal feature in all fields, including science, is that you hit a lot of bumps along the way. You fail a lot. You don't do as, like, you have a lot of bottlenecks. And what you just kind of have to do is, first, you have to be persistent. You have to kind of just like try to bull through it a little bit. And then you have to be creative. If you can't get through the wall, you have to try to climb it or go around it, or maybe burrow under it or something like that. You try to attack the problem from other ways. Maybe if you can't calculate this quantity, can you place upper and lower estimates on this quantity? Show that this quantity is beneath two different, is in a certain range, and use that to infer something. So there's a lot of trying to be clever about it, and there's a lot of trying to persevere through it. I think one of the most important things is to document everything you do, just so that record is available. And then so when you eventually try to share everything you have with the community, with the scientific community and everyone else, you can do as complete a job as possible trying to share that information.
Awesome. Well, thank you so much for joining us today. I want to encourage everybody watching to tune in on October 1st. We will be releasing the newest episode of STEM in 30, all about balloons, which might be one way that we could explore Venus in the future. We'll be talking about hot air balloons, gas balloons, all kinds of balloons, including taking a trip to the Albuquerque International Balloon Fiesta. That will be followed up on October 8th by a live chat featuring master hot air balloon pilot Bill Costin. And that'll be your opportunity to ask all of your questions about balloons to somebody that flew hot air balloons for 40 years. So we hope that you can all tune in on those two episodes. Sukrit, thank you so much for joining us, and congratulations to you and your team on an outstanding paper and all of the work that you all have done.
Thanks very much, Marty. We look forward to the scientific process continuing.
Awesome. Well, thanks for watching.